at Detroit Medical Center. Sorry, just got to pop up. Okay. During his fellowship, Dr. Mamdani obtained a Master's of Arts degree in economics from Wayne State University in Detroit, Michigan, with a concentration in econometric theory. He subsequently completed a Master of Public Health degree from Harvard University with a concentration in quantitative methods. Currently, he is Vice President of Data Science and Advanced Analytics at Unity Health Toronto and Director of the University of Toronto Temerty Faculty of Medicine for Artificial Intelligence Research and Education in Medicine, also is known as T-CAIREM. Sorry, if I can ask for those that have joined, if you can put yourselves on mute, would be much appreciated. Thank you. He is also a professor in the Department of Medicine at the Temerty Faculty of Medicine, the Leslie Dan Faculty of Pharmacy, and the Institute of Health Policy Management and Evaluation of the Dalai Lama Faculty of Public Health. He's an adjunct senior scientist at the Institute for Clinical Evaluative Sciences, ICS, and the faculty affiliate of the Vector Institute. He has published over 500 studies in peer-reviewed medical journals, and in 2010 was named among Canada's top 40 under 40. I don't know when you have time to sleep, but that is quite the CV. So thank you, Dr. Mamdani, for joining us and for presenting. I will pass it on to you.
Great. Thank you so much for the very kind introduction. I'm here to talk about applied AI. It seems to be all I'm doing these days. And then there's quite a bit of an appetite, I think, right now in the current environment, especially after that infamous ChatGPT became viral. So I'm going to talk, first of all, I'm going to actually have a disclosure up. I think this event is sponsored by Takeda. So a disclosure just to say that whatever I present are my own materials and my own opinions, and they don't necessarily reflect those of Takeda Canada. This is in French for those of you who are so inclined, but I'm going to actually now put up my own disclosure, which is I am not an oncologist. I am not an oncology pharmacist. I can barely pronounce oncology. So keep that in mind when I'm going through my presentation, although I will try and make reference to oncology quite a bit in the second, more in the second half of the presentation. My objectives are actually quite straightforward. One is to provide a general overview of AI and its implications for the diagnosis and management of cancer patients. Second is to discuss the barriers to implementation of AI in clinical practice. And the third is an overview of how I think AI will transform healthcare with examples of its emerging role in the diagnosis and management of cancer patients. You've probably seen a lot of these headlines. When do we admit Canada's healthcare system just isn't working? Wait times for medical procedures at 20-year high in Canada. Nearly 75% of Ontario doctors experienced burnout during the pandemic. 90% of nurses considering leaving the profession in the next year. It's kind of a doom and gloom type of message that we keep hearing about our healthcare system. And of course, the pandemic exacerbated that. But for decades, we've been complaining about how the Canadian healthcare system needs help. I mean, personally, I think it's a pretty good healthcare system. Of course, there's always room for improvement. We always have our challenges. And of course, the media will pick up on all the challenges that we have in our healthcare system. But every now and then, the media picks up on maybe some positive stories, like how AI is helping shorten patient wait times, which gets the attention of some people where they say, well, what the heck is this AI thing? There's lots of definitions of AI. I'm using one from Coursera. And in Coursera's definition, they basically just define it as AI is something that uses computer science and data to enable problem solving in machines. My own personal take on AI is it's all about learning complex relationships in data, how machines learn complex relationships in data. That's really all AI is. Machine learning is a subset of AI, which basically refers to computer systems that learn on their own. So traditionally, what we could do in statistical models is we could actually say, all right, statistical model, I am going to give you 12 features, and these are the relationships of these features. And I'm going to basically dictate kind of how you actually weight them and such. But machine learning says, nope, you know what, give me a problem to solve, give me a whole bunch of data to work with, and I will figure it out myself. I'm going to learn myself. That's what the computer says. And that can be actually quite good, but it can also pose a lot of questions around, well, how did you learn all these complex relationships? And often it's a bit of a black box. Deep learning is a subset of machine learning. In essence, deep learning is just more complexity, more data. That's really all deep learning is. How these things work, machine learning and deep learning, a fundamental kind of approach is using something called neural networks. So in synopsis, the way these things are structured or work is there are output layers. So basically, this is what you're trying to predict. And then there's input layers. This is what goes into the prediction. And there's something in the middle called the middle layer where it kind of figures out the relationships between the inputs to predict the outputs. So for example, if I want to predict if I want to predict if I'm going to still be alive in the next 5 years, well, what will determine if I'm still going to be alive in the next 5 years? I imagine it would be my current age, my sex, my current health status, my social networks, all that sort of stuff would predict if I'm going to still be alive in the next 5 years. And so one can say, all right, well, is age more important than if I have COPD, for example, or a particular type of cancer or whatever have you? And some of these things may actually be heavily related to each other, right? An older person with cancer, with COPD, with a lot of comorbid conditions may die sooner than a younger person who just has, let's say, asthma. And so what the middle layer does is it tries to figure out all these complex relationships to figure out what best predicts survival in the next 5 years. That's basically how these neural networks work. The more complexity you have in your data set, the more intense your middle layer is, the more you move towards deep learning models. So why is this such a big deal these days? Well, AI has received a lot of attention because over time, we've actually increased our ability to store and compute data, right? Our processing power and our compute power has increased considerably. The AI methods, the neural networks and such, they've been around since the 1950s, actually. So they're not really anything new. Now, there have been some major advancements in the methods, but I would say the significant thing that's really happened over the past few decades is improved storage and compute of data. If you look at Bill Gates' blog, and Bill Gates is pretty famous at writing about things. He tends to be fairly conservative, but he did write in his blog earlier this year, in my lifetime, I've seen 2 demonstrations of technology that struck me as revolutionary. The first, of course, is his own graphical user interface for computing, which makes computing more accessible to people. And the second is AI. Now, on the flip side, there are other people who say, some people get rich studying artificial intelligence. Me, I make money studying natural stupidity. So they go on the other end, saying, you guys focus on the AI piece, I'll focus on human behavior. If we step back a little bit, we really think about how we practice in healthcare. A lot of it is about these 3 big buckets. And of course, one can argue you can communicate as well. But the 3 big buckets in my mind are diagnosis, prognosis, and treatment. And if we think about how we make a diagnosis, some diagnoses are fairly straightforward. If you suspect a certain type of infection, you do a sputum, blood serum test, you grow cultures, you know that this is a type of bacteria that's growing. You know which antibiotic kills the bacteria. They're susceptible, not resistant. Kill the bacteria and you're done. But other diagnoses, they're kind of hard, right? And we see this in the literature quite a bit. So for example, with schizophrenia, we get that wrong all the time. Sometimes we don't even order the right test to make the diagnosis. So I'm going to use a common example of asthma. There have been several studies now, one in Ottawa, for example, that brought in over 600 patients who were being diagnosed, were diagnosed with asthma, and over 80% of them were being treated for asthma. And they brought them back and they said, I'm actually going to do proper spirometry, lung function tests, and actually see if you actually have asthma. And about a third of patients did not have asthma, yet they were diagnosed as having asthma and being treated as such. So we often struggle with making a correct diagnosis. And oftentimes it's actually processing all the information that you need, because you have to consider things like social history, family history, labs, vital signs, medical imaging results. All that sort of stuff has to go in your brain to figure out what that diagnosis is. Let's say you make the right diagnosis. Okay, now we're going to talk about how you manage that patient. How you manage that patient is going to be dependent on how well you think that patient is going to do or not do. If you think they're going to deteriorate quickly, you're going to be very aggressive in your management, right? You may pick therapies that maybe have considerable side effects, but you know they work. Versus if the patient isn't going to do so badly, you may be a bit more conservative in how you manage your patients. So you may actually say, I'm going to pick something that's a bit kind of gentler. But how do you actually base that judgment? You actually kind of guess how the patient is going to do. And oftentimes, yeah, you kind of guess how the patient is going to do. It's your gut feel, it's your experience. Study after study after study has shown how poor we are at prognosis. We're just not very good at it. And yet that defines the treatment strategy, right? And of course, cancer has, or oncology has pretty good defined protocols and such around treatment regimens and such. A lot of other conditions don't. So for example, if we take a common diagnosis like depression, we have lots of agents to choose from. SSRIs, SNRIs, TCAs, MAO inhibitors, and such. We probably have about 15 or 20 drugs, if not more, to choose from when it comes to management of depression. How do we pick? Oftentimes, it's, I'm kind of used to using these meds, or the drug rep that came in 4 months ago told me about this one. And of course, we then pick it based on our kind of gestalt, try it, call the patients back in 2 to 4 weeks, see if they've done any better. And if not, you try something else. Kind of how we do things. And many would argue there's a better way to do this. This often boils down to processing, again, that massive amount of data in your head and making a decision. There's over 30 million studies that have been published in PubMed. There's no way we can keep on top of them. And again, the amount of volume that we have to process can be really, really daunting. There are people who suggest that the modern complex medical decision involves considering hundreds of parameters. Some estimates are up to 1,000 parameters. Yet the average human can process 7 plus or minus 2 things at the same time, as shown by Miller in the 1950s. So again, need to process hundreds, capable of processing 7 plus or minus 2 things at the same time. That's tough, right? And what does that mean in terms of the quality of care? 25 to 40% of patients get treatments of unproven effectiveness or are even potentially harmful. So there's a lot we could do to improve. We do a lot of things really well, granted, but there's also a lot of areas where we can improve. So how do you get from research to practice? There's a lot of research being done in AI these days, and machine learning in particular. So if we look at just maybe about not even 20 years ago, there may be a couple hundred papers that were published in PubMed. Now, typically, there's about 15,000 or so that are being published annually. So a lot of activity. And this spans all sorts of areas, from pathology to oncology to gastroenterology. Most areas in medicine have some sort of work been done in the AI field.
No. Yeah.
What about getting things into practice? Well, if you look at FDA-enabled, AI-enabled devices approved by the FDA over time, literally about 15 years ago, there were only a handful. Now there are hundreds. I'm guessing there's around 500 or so FDA-approved AI or machine learning-enabled devices that are available on the market today. And we're going to see many, many, many more come up in the near future. And that's also driven by business factors. So if we look at the healthcare market size, it's pretty substantial for AI. In 2021, it was about 11 billion. It's estimated to go up to about 200 billion by 2030. So there's a lot of incentive for companies, for organizations to actually invest in this area and pump out more solutions, because the general feeling is AI can actually really, really help. But how do we actually get there? There's a lot of really neat papers, a lot of really great, miraculous things that AI can do. But when you actually go to deploy these things into practice, it's tough. It's really, really tough. As we know, knowledge translation is not easy in healthcare because we tend to be quite conservative for very good reasons. So how can we learn from data science failures? And there's a lot of them out there. I'm going to first talk about Microsoft Tay. Many of you may have heard the chatbot Tay. Basically, in 2016, Microsoft came up with this brilliant idea. We have this chatbot that is so good. It's so good that when people are going to talk to it, they won't even know it's a chatbot. They'll think they're talking to a human. Well, how are we going to mimic human language? Well, that's easy. We'll get it to talk to humans, so it'll learn all the slang terms and the lingo and all that sort of stuff. So it'll see more human because it's learning from humans. Wonderful, brilliant idea. All right, so why don't we put this thing up on Twitter? That was what they came up with. They said it'll go on Twitter, it'll start interacting with humans, it'll learn how they talk, and it'll be wonderful. Great. So they put Tay on Twitter, and within 24 hours, they had to aggressively pull back Twitter because the Twitter trolls jumped on Tay and taught it to be extremely racist and misogynistic. And how did that happen? Well, the Twitter trolls are going to feed it a lot of garbage, and it's going to learn a lot of garbage, and it'll spit out a lot of garbage. So if you give it really, really bad information, it's going to learn that information. It's going to spit that right back out. There's another example. Somebody's on Swati, maybe. Yeah, there you go. All right. There's also other examples, like, for example, in Thailand, the government approached Google because Google had this algorithm that would be able to detect diabetic retinopathy. So eye disease among patients who have diabetes. And it does it quite effectively. It was able to perform just as well, if not better, than world-leading ophthalmologists in detecting diabetic retinopathy, which is excellent, right? So the government in Thailand calls up Google and says, hey, we have this massive screening campaign, and we want to be able to use your algorithm because we're not staffed sufficiently to be able to do this on a national level. So could we use your AI algorithm? And we're going to detect diabetic retinopathy across the country. And Google said, yeah, that sounds great. So they start deploying this algorithm into clinics in Thailand, and they quickly realized the algorithm was trained on really good, clean research data. About 20% of images in real practice were done under poor lighting conditions. And that's not what the algorithm was trained on. So it started failing. Patients started getting rescheduled. Everyone was upset, and they had to pull it out. So again, on the one hand, you can have garbage data and the algorithm will perform very poorly. On the other hand, if you have really good clean data and it's not reflective of how you practice, it's going to fail there as well. So again, some learnings that people were trying to take up to say, all right, what is that middle ground of actually developing AI algorithms that work well? So this is why when people say, I've got a cool research project, I'll say, okay, that's good. I'm not really sure if it's going to be able to be translatable, to be quite frank, because chances are you use data that either don't exist in the real world or they're just too clean. And it's just not going to work when you actually go to apply it. There's also other studies that have done systematic reviews. For example, there's this one that was published a couple of years ago, where they looked at over 400 studies that were published during COVID. And they were on AI solutions that people thought were going to change the world. The lens they took, though, was, can these solutions actually be deployed into clinical practice? And when they took that lens, after reviewing over 400 studies, they found 0 could actually be deployed into clinical practice. So again, really great research, all for it. But it takes a lot more than that to actually do something that's translatable into clinical practice. So I'm going to go through a case example of how we've approached AI at our hospital, in our institutions. So I'm from Unity Health Toronto, and Unity Health is composed of St. Michael's, St. Joseph's, and Providence Healthcare. We have over 11,000 staff, over 5,000 medical trainees, over 1,500 physicians. We have about a little over 1.5 million ambulatory visits each year, over 170,000 emergency department visits each year, and over 350,000 inpatient visits each year. Why am I giving you these volumes? If you multiply that by about 15 years of historical data, that's a lot of data to play with. The other thing that we've done at Unity is pretty progressive. We've actually declared AI as a core strategic pillar. We have 8 strategic pillars. 3 of them are core pillars, and AI is one of those core pillars. So from top down, it is a priority at our institution to invest and to leverage AI. What does that mean? I get a dedicated team. So I have a data science team of 30 data scientists, and we've developed and deployed over 50 solutions into clinical practice. So we have quite a few of these things running around in our hospitals, making a difference for our patients. How are we structured? So the 30 data scientists that I have are parked into 4 teams. And the first team is data integration and governance. This is the bulk of the work. you can't do AI without data. And so we actually have a team dedicated to data engineering, ETL development, modeling, data modeling, architecture, that sort of stuff. So they focus on how do I get data out of my systems in a manner that's going to be amenable to AI? And how do we do it in real time? Because the research play is easy, right? Research, you got a compute environment, you got a data environment, and you've got a data set to play with, go and play. In practice, if you want to deploy these things, I need to actually get real-time data feeds from source systems into a central place, clean it in real time, process it through a machine learning algorithm in real time, spit it back out, and get the output and give it back to the clinicians all in real time. That's really hard. And so you need a whole team dedicated to what's called machine learning operations and a DevOps environment that'll actually enable all of that. Then you go to the second team. The second team is the advanced analytics team. They do the modeling. So they build the neural nets or optimization algorithms or whatever it's needed to solve that problem. So they focus on the modeling side of things. And then, of course, once you have a model and you go and say, all right, here's my results, most clinicians will not be able to interpret output from a machine learning model. So how do you take that output and turn it into something that we can understand and that we can use in clinical practice? Well, we have a team focused on product development. This product development team is headed up by somebody who is an artist by training, but actually went and did a Master of Science in Applied Computing. He can develop models, but his passion is how do humans interact with AI? How do I actually build a solution really understanding people's workflow, design considerations, human factors considerations? He has a team that has software developers. How do I actually really understand what people need and what will work in their day-to-day? And of course, the fourth team is product management and deployment. This fourth team is really responsible for getting the other three teams together and really liaising with our end users. So our clinicians, our frontline staff, those are the people that really are going to be deploying these things and using it. We have a whole team dedicated to really bridging them, bringing them in, bridging our group with theirs, and really having a co-creation approach to solutions, which makes all the difference in the world. So they have expertise in product management, project management, and also change management and deployment. So how does the model work? Our model is very simple. Researchers don't get to ask questions. Our team, data scientists, don't get to ask questions. End users, so frontline staff, clinicians, decision makers, they get to ask the questions. They don't have to know anything about AI. All they can do is say, I've got an issue. I think AI can help. We want to talk to you. So how does the process work? They come in and we get to fill out an intake form with them. What does the intake form look like? There are several components to the intake form. The first component is, tell me about your problem. What are you struggling with right now? And we want numbers. How big is the problem? And if you don't have numbers, we can try and help you get them, but we need to understand the magnitude of the problem. Next section says, all right, tell me how you're going to address it. How would AI help and what sort of interventions do you have that would be able to change the current status? Once you explain that to us, we then go to the next box around outcomes. We focus very much on particular outcomes, and you have options: mortality, readmission, length of stay, human effort, cost, and other. And if you click other and that's the only box you click, you're automatically deprioritized, because we really want to focus on those hard metrics that people want to see. And then, of course, we ask you for a number. If you clicked on mortality, tell us by how much. And you have to tell us, I'm going to drop mortality by 10% if we're able to do this. Great, because that's what we're going to hold you to. Because when we actually then co-create the solution with you and we deploy, we're going to evaluate. And if we don't hit that 10% reduction in mortality benchmark, we either sunset the solution or really do a deep dive in terms of why aren't we achieving the metrics we thought we would. So again, a very structured approach in terms of how we take in projects, how we think through them, how we co-create. Because the person who actually suggested this is a really good idea, we need them to sit with us. They attend meetings every 2 weeks. We meet with our data scientists, our clinical teams. Every 2 weeks, we're meeting for 6 months to a year. And they have to commit at being at every one of those meetings because they actually lead many of these meetings. They have to be fully engaged. Right? And if we don't have that level of commitment from our end users, we don't do the project. Examples of deployment. So I'm going to go through a few. One is around optimization and automation. So our nurses came to us from the emergency department, and they said, here's the issue that we struggle with. We struggle with assigning our nurses to the different zones in the emergency department. Why? Because there are all sorts of rules. A junior nurse has to be with the senior nurse, can't be with, and has to be with the team lead as well. Can't work, two nurses can't work in the same zone within a 48-hour period of each other. There's all sorts of rules that we have to adhere to. And they told us that it takes 2 to 4 hours every day doing this task. And their error rate or repeat rate is over 20%, which is ridiculous. They should have more time to be doing clinical things and spending time with patients and doing more useful things. So we created an optimization algorithm with a software solution where basically it's a fairly sophisticated optimization algorithm where it basically, quote unquote, watches all the nurses. So it knows who worked where, when, with whom. And all you have to do is click a button and it'll set your assignments for the next 4 days. If somebody calls in sick or there's an issue, you call up that name, say sick or issue, you click again, it'll reassign everybody. So we've noticed after we deployed this solution that human effort went from 2 to 4 hours every day to under 15 minutes. And the error rate or repeat rate went from 21% to just under 5%. Again, something that's driven by AI using fairly sophisticated optimization algorithms. Another example is medical imaging. So one of the other issues that I know we struggle with a bit is intracranial hemorrhage detection. Especially at centers that don't have neurosurgical supports like we do. At our institution, even though we have 24/7 neuroradiology coverage, it took us on average about 3 to 4 hours to detect a bleed on a head CT. And time is brain. So we have an algorithm now that's been running for a little bit that what it does is it actually listens for the head CT in the emerge and is able to say, yep, there's a bleed, here's a subtype, and here's where it's located. It takes about 28 seconds. It's got over 94% accuracy. And what it does is once it detects a bleed, it identifies that patient. And in the radiology information system, it color codes that patient as purple and moves them right to the top of the radiologist queue. So they look at it now rather than 3 or 4 hours from now. And it just means faster time to diagnosis. The last example I'll give is ChartWatch. What we've done at St. Mike's is on our general internal medicine unit, we've expanded to a surgical unit. We're expanding to more units and to St. Joe's very soon in the new year. One of the big problems that our internists raised was that people come to the hospital to not die. So how can we help them? We know that 1 out of 12 patients will die. And for many of these patients, there's nothing we can do about it. No matter what you do, they will die regardless. But for quite a few of these patients, you know, we could have done something if we had known, if there was something that alarmed us. Because on average, physicians will spend maybe 5 or 10 minutes per patient per day, maybe. And then the rest of the time is managed by nurses who are incredibly busy and have a million things on their plate. So how can you possibly keep an eye on somebody and process all sorts of complex information to look at prognosis? So we have something called Gemini. It's been up and running since October of 2020. So we have about 3 years of experience with it now. What ChartWatch does is it grabs data every hour on the hour for each of our patients. So it typically focuses on demographics, labs, and vitals. And nobody has to enter anything. It just does it automatically. It categorizes patients as low, medium, and high risk, and it predicts if that patient is going to die or go to the ICU in the next 48 hours. As soon as it reaches a high-risk threshold, it's automated to page the medical team. And our protocol is the medical team has to come and see the patient within 2 hours of being paged. So again, and it has all sorts of care pathways. Do you increase monitoring to Q4? Do you look for signs of sepsis, initiate antibiotics? We spend a lot of time. There are early warning systems that are out there. So for example, there's News out in the UK. We actually spent quite a bit of time on the floors, and we actually surveyed our physicians, our nurses, and our residents. And we asked, do you think this patient's going to die or go to the ICU? Because that's who the algorithm is competing against. It's clinician opinion. We were able to collect over 3,000 clinician predictions. And what we were able to show that a solution like News from the UK our clinicians beat news, not by a little, by a lot. So we would never deploy news because it's just not useful. It's going to irritate our physicians because it's not telling them things that they don't already know. They're actually outperforming news pretty soundly. If you look at ChartWise, the sepsis solution in Epic, for example, similar thing. It doesn't really perform that well. So we actually had to create a solution that would beat our clinicians. And we've actually published a paper on this. This solution actually, plus clinician judgment, is better than clinician judgment alone. So what are we seeing in terms of mortality reduction? We finished our analysis and we're seeing a greater than 20% reduction in mortality because of this monitoring. So we're fairly happy that these things not only save time and energy and resources, but they also save lives. What are some considerations? When we go to pre-implement, there's all sorts of things that we do in terms of bias assessment, for example. We'll assess to say, all right, well, does this algorithm perform just as well among young versus old, among males versus females, among sick versus not so sick? And it generally holds up. Do we know about race? No, we don't, because we don't have race data. Do we know about gender? No, we don't. We don't have gender data. Do we have socioeconomic status data? No, we don't. So how thorough is our bias assessment? I would say it's moderate at best. It's not that thorough. Would I like it to be more thorough? Absolutely. Is it unethical for us to deploy an algorithm that hasn't been run through the paces in terms of bias assessment? I would argue some people would say it might be. But at the same time, I would argue I can pull the algorithm, wait for race data, and let 20% more people die. Is that ethical? So there has to be some practicality around how we look at bias assessment and what level of rigor. Because I can guarantee you, if I go to a conference and say, I've done bias assessment on 40 parameters, somebody's going to raise their hand and say, what about 41, 42, and 43? There's over 100 genders. Am I going to be able to get at those? Probably not. So we have to be practical in our approach to bias assessment. Some of our algorithms have very sensitive issues in terms of need ethical review. And that's something that we also do. It's great to actually have an ethicist who will step back and say, wow, this is actually a real case, not something I'm reading about, but what's actually happening, which raises a whole set of issues that maybe you don't see as much in the literature. Communication and clinical validation, we spend quite a bit of time on that. Because again, if your algorithm is competing against physician judgment, and that's what we often compete against, you need to measure how good or bad they are. And what we're able to show with ChartWatch is that when a physician says this patient's going to die or go to the ICU, they're right less than a third of the time. Right? So we're not very good at prognosis, and we know that. But for the arrogant people who say, oh, I know this, I'm really good at it. Actually, in many cases, you're not. and we can show you you're not. This is why it's okay to say I need help. And that's what I think AI is intended to do. There's all sorts of talk around external validation and explainability. External validation is really important if you're going to deploy at other sites. But if you're doing work at your own site, the algorithm has to perform well at your site. External validation isn't really that important in that case. But if you're deploying to many other sites, it becomes critical. Explainability. People always ask, how do these things work? How is this algorithm able to predict X when I'm not so good at it? And I'm a clinician. Well, it becomes complicated because we can give things called Shapley values or SHAP values, which basically go, these are the key drivers of why the algorithm says this patient's not going to do well. They tend to be quite linear and quite limited. And so most clinicians will say, I already know this. So it's not very helpful. It's really the complexity of all sorts of parameters working together that's going to cause a deterioration that we may not have the cognitive load to pick up on when we're so busy doing so many things. That's the power of AI and machine learning algorithms. And when people say, I need to understand everything in order to use it, Leo Celli, who's over at MIT at Harvard, and I love what he says. He actually asks a lot of clinicians. He's an intensivist at Beth Israel. And he asks a lot of his clinician colleagues, do you use acetaminophen? And of course, many people will say, yes, of course I use acetaminophen on my patients. And he asks, can you tell me the mechanism of action? Of course, nobody can because we don't know the mechanism of action. Yet we use it because it works, right? So I think we have to kind of step back and ask ourselves, well, why do we hold other things to such different standards? We do a lot of silent testing, soft launches. So basically, this is putting the models into production without really the clinicians knowing, just to kind of see the data pipelines aren't failing, the model is performing as it should before we actually fully deploy. Really important to do silent testing. And of course, evaluation. If things are not working well, we should know about it. But more importantly, if things are causing harm, we should know about it. And of course, implementation and post-implementation, there's always a lot of communication. But monitoring, evaluation, and maintenance is really key. Because a research project says, here's a cool algorithm. It's a model that works. Yay. Wonderful. What happens? Does the model degrade 2 years from now? Are you seeing data shifts that are actually really, really messing up the model predictions 2 weeks from now? Who's going to fix any data pipeline failures? So our data scientists are on call 24/7 because these issues come about. And somebody's got to fix them, especially if the organization is reliant on these algorithms. So there is a little village that's needed to be able to develop, deploy, and maintain these algorithms to actually gain clinical benefit. There's a series of papers that we published just based on our experience in terms of implementing machine learning. Amol Verma, who is the first author here, is the mastermind behind ChartWatch, and really it's his initiative that really drove that adoption and reduction in mortality that we're seeing today. There's one that's more focused a little bit more on methods and models, and then on evaluation of how you actually evaluate these things in clinical practice. Our approach, in very brief summary, is very simple. A lot of these institutions, academic centers, will create AI labs. And those are fairly easy, relatively speaking, to create. You've got researchers who want data and want to do research. Wonderful. You've got an environment that houses data and has enough compute power. Great. That's not that challenging compared to having a living lab. The living lab changes the game. What it does is it says, researchers, that's fine, you do your thing. We're going to focus on the end users. Clinicians, the frontline staff, that's what we're going to focus on. They get to play. We're also going to have a very progressive data governance framework that enables data scientists to have access to very sensitive data. Because I can't deal with de-identified data. I need identified data. If I'm going to tell you Mr. Jones is the one who's going to die in the next 48 hours, I need to know it's Mr. Jones. So how do you enable that through a data governance framework? And of course, machine learning operations, very different from a research compute environment. MLOps is fundamental, foundational. How do you actually have a good functioning MLOps environment to enable real-time data feeds? Some of our algorithms are updating every 15 seconds. How do you enable that? And that's a whole different ballgame. Then, of course, there's the last piece around the AI accelerator. So something we failed miserably at is how do we get our solutions to other hospitals? We failed miserably because we actually tried to work with a few other hospitals and quickly learned many hospitals don't have the knowledge base that you need around machine learning. They don't understand the outputs that are generated. They don't have software developers and solution developers. We actually tried to deploy a solution at 6 other hospitals. We ended up being their IT help desk and support, and quickly realized we're not positioned to do that well. So last year in April, we launched Signal One, which is a startup. Unity actually has a strong partnership with Signal One. And they basically come in and really dedicate their time, energy, and efforts to actually productizing some of the solutions that we create and then bringing them to other hospitals. And we're thinking from our experience, that's really the one major way to do things is to have that private-public sector collaboration to scale AI solutions. At least that's been our experience. What are examples of AI research in oncology? Lots of stuff out there in terms of looking at algorithms that will predict on mammography breast cancer risk. And I think these guys looked at 5-year risk of developing breast cancer on a standard mammography and performed reasonably well, better than existing indices. Then there's, of course, real-time computer-aided detection of colorectal neoplasia. And this was a randomized trial that was able to show that there was a 30% increase in the rate of adenoma detection when real-time computer-aided detection algorithms were used involving machine learning. And of course, how do we actually use it to help us with drugs and medications and such? So this actually algorithm predicts lapatinib dose regimens using machine learning in breast cancer. There's also algorithms around predicting toxicity, for example, in terms of platinum-induced nephrotoxicity in non-small cell lung cancer patients. At Sunnybrook itself, actually, there's a group who was able to develop an algorithm that predicts response to chemotherapy in breast cancer with 96% accuracy. There's wonderful work that's being done, and I really hope some of these algorithms come into clinical practice to help guide clinical care. I'm going to talk a little bit about generative AI because, well, everybody's talking about ChatGPT these days. Generative AI is basically a subset of AI that where machine learning algorithms and models are enabled to use existing content like text, audio, video, files, images, and even code to create completely new content. ChatGPT is what we're used to hearing because we talk about text, we type stuff in and we get stuff out. That's text-based. Think about ChatGPT for videos. So you can actually feed it a video and it'll actually create a whole other video. I was actually asking my team, how long would it take for you to generate a video of me giving a lecture on generative AI for 1 hour, a lecture that I have never have given? But if I let you listen to my voice for 10 seconds, if I looked in a webcam for about a minute and it looked at my facial expressions and how I move and how I talk, how long would it take? They said, give me 10 minutes. I'll come up with a video of you giving a lecture for an hour on generative AI that I will never have given. And chances are you won't even know it's not me. That's the power of generative AI. These are pictures of people that don't exist, right? So AI was asked to create realistic pictures of humans. They look pretty good to me. So its capabilities are actually pretty impressive. And then, of course, how about applications of generative AI in oncology? So can you ask ChatGPT to prepare the patients for PET and CT and explain the reports? Apparently, you can. And it's not too terrible in terms of how it performs. In fact, response rates here were rated as appropriate for 92% of 25 tasks and useful for 96%. What about chatbots? So to provide genetic information to patients at risk of hereditary breast and ovarian cancer. A qualitative study suggests while it can't replace genetics counselors, it can certainly aid them. And because of the shortage of staff, really assist in this process. Then, of course, there's studies out there that have actually looked at how physicians compared to AI chatbot responses to patient questions that are posted to public social media forums. And the interesting part is when they actually looked and compared, the chatbot responses were consistently rated as being of significantly higher quality than physician responses and more empathetic than physician responses, which was kind of interesting. Of course, there's all sorts of limitations and challenges to this study, but what it raises is the possibility of using these chatbots in ways that maybe we haven't thought about, which I think could be exciting. And of course, there's also a lot of work going on around things that we love to do, right? Charting and writing discharge notes and summaries and all that sort of stuff. Can we use AI to automate the discharge summary hospital course for, let me hear it's neurology? Why can't we do it for other disciplines? Of course we can. Is it going to be perfect? Absolutely not. But is it going to decrease our workload considerably? I think so. There's a lot of potential for that as well. So more of the administrative side of things. One of the key concerns, though, is hallucinations. AI, these chatbots and generative AI makes up stuff. And it makes up stuff in such a convincing manner that you won't even know that it's not real. So that's one of the big limitations of generative AI is I don't think we're there yet in terms of having a low enough hallucination rate for this to be really, really usable in many things. I think we're going to get there. But right now, it does make up stuff in a very convincing fashion that can be quite concerning. The other risks here is earlier this year, a man committed suicide in Belgium because a chatbot encouraged him to do so. So very concerning around how chatbots can then can be so quote unquote real to people that they feel like they're their friend. And we're getting closer and closer to, some would argue we've already passed the Turing test in terms of these chatbots being as close to humans as once envisioned. I still think we have a little bit of ways to go, but we're getting there. This is why we're seeing generation of these more kind of institutes that focus on responsible AI, and how we set some guardrails around what we do and don't do with AI. And of course, that's why public perception is also being a bit tempered, right? There's a Pew Research Center study that was conducted last year of over 11,000 US adults. And 60% of them said they were uncomfortable with a healthcare provider who relied on AI to do something like diagnose their disease or recommend a treatment. 79% said they absolutely do not want AI involved in their mental health care. On the flip side, though, 65% of those surveyed said they're comfortable using AI to detect skin cancer, and about 40% said AI can help providers make fewer mistakes. So I think the public's maybe a little bit confused in terms of what AI can and can't do, but there is this caution around AI. The last thing I'll pitch before ending is people sometimes get excited about this and they want to learn more. I'm all for it. I think people should learn as much as possible. There are networks that exist. At the University of Toronto, we have the Temerty Center for AI Research and Education in Medicine, or T-CAIREM. It is free to join. There's no cost. There's lots of benefits. We received a very generous donation from the Temerty family to make this happen. So anyone who's interested, we have a community of healthcare providers, statisticians, computer scientists, engineers, all sorts of folks who are interested in advancing AI in medicine. We have a community of over 1,200 members. 25 Canadian universities are in our network, over 90 healthcare organizations. In terms of research, we typically offer about $700,000 to $1 million a year in research funding opportunities. In terms of education, we have all sorts of education activities, from speaker series. We had Eric Topol give us our first talk during our speaker series, world-renowned experts. We have trainee rounds. 80 to 100 trainees typically attend these rounds, from medicine, engineering, computer science, statistics, all very multidisciplinary. Last year, we were able to give out 29 summer studentships. This year, we're giving out, next year, 2024, we're giving out 30 to support this sort of work. And infrastructure, we have created Health Data Nexus on Google Cloud, which basically gives people unlimited storage and virtually unlimited compute for research, for education, for teaching purposes as well. All that is available through T-CAIREM. So again, I would say that if you're really interested in learning about this, go to our education hub at T-CAIREM. There's all sorts of tailored hub resources that you can leverage, from videos to book recommendations to all that sort of stuff to learn more. And last year, we were awarded 2022 AI Med Institution of the Year internationally as being the leading center globally, which was really exciting for all the work that we've done at the University of Toronto. So we're very fortunate to be in this environment where we actually have excellent skill sets, both in healthcare as well as computer science and engineering, making this a fairly unique place internationally. So the other thing that I'll say is, in addition to our national network, we have an international network as well. We've got MOUs with Technion University in Israel, as well as the Indian Institute for Information Technology in Delhi in India. And we're going to continue to expand our relationships globally as well. So please join if you haven't already, if you want to learn more about AI in medicine. And I will end there, because I think this is the way forward that we can provide better care for all of us. Thank you.
Thank you, Dr. Mamdani, for that